Hello, this is Mr. Tuxford, and we're just going to go through the electromagnetism section of Level 2 Physics. Alright, in the past two videos we covered electrostatics, and then DC circuits, and now, oh my goodness, and now electromagnetism. So the main topics, again disclaimer, not all of the topics, but the main topics within electromagnetism are current and magnetism, right, how they're related through the right hand grip rule, force acting on a wire, F equals BIL, force acting on a charge inside a magnetic field, F equals BQV, induced voltage, V equals BVL, and to support sort of the explanations for that and the direction of the force acting on the charge or the current, right hand grip rule, right hand slap rule. Yeah, and in particular we'll focus on how the right hand slap rule explains force on a current, force on a charge, and how we use it to find the polarity for an induced voltage. Alright, so current and magnetism. You may know, if we have a current flowing through a wire, it creates a magnetic field around it. In this simple example, it would be using the right hand grip rule. I'm just going to paraphrase, right hand grip rule, because that's a lot of letters to write up. Right hand grip rule. Our thumb points in the direction of current, so to the right. Our fingers curl towards us above the wire, so it's coming out of the page above. As it goes over the wire and under the wire, when it's under the wire, our fingers would be pointing into the page. So get your hand out, make sure this makes sense to you. Your right hand thumb points to the right in the direction of current. Your fingers curl, right, like you're giving a thumbs up on the side. Above the wire, they point towards you. They curl down. Below the wire, they point away from you. So dots mean towards, right, or out of page. A cross is away from you, right, or into the page. And we need to use this dot and cross notation because, right, we're dealing with paper, which is two-dimensional, but we're representing something that is three-dimensional. Alright, so that's current and magnetism. You may have learnt last year that if you increase the current, the magnetic field strength around the wire increases. You may also know that the further away you get from the wire, the weaker the field is. So very close, we'd have a lot of field lines, and the further away we get, as distance increases, the magnetic field strength decreases. Right, that's just for a wire. Alright, now let's look at force acting on a wire. Now this is a wire with current, so you know it'll be connected to some circuit somewhere, and it is inside of an existing magnetic field, right? An external magnetic field. So that could be provided by, for example, like a horseshoe magnet. Maybe you have a, big horseshoe magnet, north-south, and you pass a wire through it. So you'd have field lines going north to south. Yeah. In this example on the left, let's just suppose the external magnetic field is into the page and current is down. So we know from the right hand grip rule that this current will create a magnetic field around it. So let's draw that in. So by right hand grip rule, our thumb points down. So our fingers curl. I'm not even going to try to draw that. So our thumb points down. On the left hand side of the wire, our fingers go into the page, right, with crosses. It goes back behind the wire On the right hand side, it comes out of the page. So in red is the magnetic field produced by the wire. In blue is the external magnetic field, for example, from a horseshoe magnet. Now notice on the left side, the fields are going in the same direction. So they would add together. Right, this bigger X is just showing how the field strength would increase at that position. Whereas on the right, they're in the opposite direction, so they would get weaker. So maybe I shouldn't remove it. They would get weaker. And so this imbalance in the field strength actually results in a force on the wire. And to determine the direction of the force, in this example, think of the green X's as sort of like increasing the slope of the hill. So you have, bear with me. This will help, this will blow your mind. So in the middle we have the wire. On the left, we've increased the height of the hill, the strength of the magnetic field, whereas on the right, it has now decreased. So if you're in the middle, you're going to want to roll down the hill. You're going to want to go towards the side with the weaker magnetic field, which in this case is to the right. So this wire will experience a force to the right. Cool. So that was the full explanation. Let's now look at the right-hand grip rule, which actually simplifies this. Right, so that's the physics behind it, but let's just, consider right-hand grip rule. Boom, boom, boom. Current down, field into the page. Right-hand grip rule. So get your right hand out. Oh, here's mine. Beautiful. Oh, look at that. Oh, that's not too bad. What the? So your right hand, your thumb points in the direction of the current. So in this example, right here, your thumb points down. So get your right hand out. Make sure it's flat, like you're about to slap someone. Oh, I meant right hand slap rule. You're about to slap someone, right? It's flat. Your thumb points down. Your straight fingers, not curled, your straight fingers point in the direction of the magnetic field, which is into the page. And what direction does your palm point? Well, if you did it correctly, it should point to the right, because the force acting on the wire, F, will be to the right because of the reasons we discussed before. Yeah, so that is the right hand slap rule. Here's another example for you. We have current going to the right. We have magnetic field out of the page. What's the direction of the force? Current right. So thumb goes right. Fingers out of the page. Palm is pointing down. So the force will be down. You may even get one where current, let's say, is coming out of the page. Magnetic field, let's say, is going to the right. What's the direction of the force? I'll give you a moment. So current's out of the page. Magnetic field is to the right. Force would be up. Upwards. What if current is going right and magnetic field is going right? Let's use green for magnetic field. What would the direction of the force be on this wire carrying current? Since there is no component of the field that is perpendicular to the current, there will be no force. Right? When current is parallel to field lines, there is no force. there is a maximum force when they are perpendicular, which is, I guess, typical of a level 2 question. So that is right hand slap rule and force acting on a wire. So maybe just an example with numbers. So let's look at this example again. If the field strength was 2 Tesla, that's a very strong magnetic field strength. And if the current was 1 amp, and now this length, it's not the total length of wire, because the wire could run on for ages, right? It is the length of wire carrying current inside the magnetic field. For example, if we do a top-down view of this one, let's make this our current. So top-down, and this is our magnetic field. Let's say the magnetic field only extends as far as this box. Even though the wire continues on in both directions, the length is just the length inside the magnetic field. And let's say that's 1 meter. So in this example, the force acting on the wire, or the part of wire inside the field, is the field strength times its current, 1 amp, times the length of wire inside the field, which is 1, giving 2 newtons. Are we done? Nope. Force needs a direction as well. Back to this diagram, right, it was upwards. If it was this diagram, what would it be? Current is right, so thumb is right. Straight fingers are up, palm is out of the page. So in this diagram, we would say the force is out of the page. All right, let's move on. So we've got F equals Bill, we've got force on current, force acting on a charge. So what is current? Well, current is just charge per time, right? Flow of charge. So in fact, it's the force acting on the charge. And when it's a current, of course, the whole wire would experience that force. So here's a scenario. We have a magnetic field. Here we go. Is it into the page, out of the page? Crosses into the page. Let's say we have a positive particle. Could be a proton, or it could be an ion, for example, like an alpha particle or something. It is moving with some velocity to the right through a magnetic field, right? And it has some charge. This positive charge will experience a force equal to the product of the field strength, the charge, and its velocity. Right? So if we increase any of those three things, it will experience a greater force. Now, we know force has a direction, and we can determine the direction with the right hand slap rule again, but this time for a charge, specifically a positive charge. Now, the negative charge, you could use the left hand slap rule, but I recommend, to keep it simple, use the right hand slap rule, but then reverse the direction if it's a negative charge. So, looking at this, our thumb points in the direction of the velocity of the charge, right? Where is it heading? Our straight fingers, remember it's a slap rule, so our fingers are straight, point in the direction of the magnetic field, and our palm points in the direction of the force on the charge. So in this example, our thumb points to the right because the positive charge is moving to the right. So that's just like current, right? Current is the flow of positive charge. Here, the positive charge just isn't in a wire. So it's moving to the right. Our straight fingers are into the page, magnetic field is into the page. And our palm, if you do it, so put your straight fingers into the screen, your thumb points right, your palm ends up pointing up. And so the force on this positive charge would be up. And so what would its trajectory look like? Well, if the force is up, it will accelerate it up. So its velocity will change direction, and its trajectory would actually look something like that. Well, if the magnetic field was up here, it would end up being a circle. Yep. So that force, since it is perpendicular to its velocity, it is actually a centripetal force. Right? You know that from mechanics, an inwards force, causing it to follow a circular path. And of course, the radius of that path will change depending on the field strength, the charge, and the velocity. So recall mechanics, Fc equals mv squared over r. So you could equate bqv to mv squared over r and solve for some unknown. Or use that to explain how the radius changes if you increase the velocity. Cool. So bqv equals mv squared over r. 1v cancels. bq equals mv over r. If you rearrange for r, r equals mv over bq. So as the velocity goes up, the radius of its path would also go up. Cool. And that could be an excellence question, exploring that relationship. All right. Have we missed anything here? Right-hand slap rule, force acting on charge. I guess let's have a look at a negative charge. Yep. So let's do field coming out of the page. And we'll have a negative charge going up. What will the direction of the force be on this charge? So right-hand slap rule again. Thumb, point in the direction it's moving, but remember at the end we need to reverse the force. So thumb goes up, fingers point out of the page, my palm is pointing right. So if this was a positive charge, it would be pushed to the right, but since it is negative, we know it will be opposite. So it will be pushed to the left, and so its trajectory would look like that. Cool. Done that. Looked at right-hand grip rule at the start, force on a charge, and lastly we're coming to induced voltage. So induced voltage, V equals B lowercase b, capital L. Oh, look at that, we're almost at the exam question. Oh, exciting, that's your homework. V for voltage, B for magnetic field strength, lowercase v for velocity of the conductor with length L inside the magnetic field. For example, the question you're about to try, we'll do something a little bit different, so as to not spoil it for you. You're welcome. Oh my, hello, pen. Okay, that's gone. Hello, sorry. Back to induced voltage. When we move a conductor through a magnetic field, for example, let's just have a conductor. Let's make the magnetic field out of the page. This isn't attached to anything, right? It's not part of a circuit, no currents flowing. It's literally just a chunk of metal. If we move it, so that we're pushing it somehow, through a magnetic field, what's going to happen? Well, consider a positive charge right in the middle. Disclaimer, the positive charges, the protons, don't move. right? It's the electrons that move, but the convention is for right-hand slap rule that we follow a positive charge. So keep that in mind. Let's follow a positive charge. That positive charge, like in our example here, when it moves through a magnetic field, it experiences a force. So what's the direction of force on this positive charge? So it is moving to the right, so thumb goes to the right, magnetic field is out of the page, fingers come out of the page. Where is your palm pointing? It's pointing down. So this positive charge is pushed down, or in reality, right, it's actually the negative charges that get pushed up. And so we have this difference of charge. We have positives at the bottom, hello, and negatives at the top. A separation of charge like this is called a voltage. So by moving the conductor through the magnetic field, it pushes the electrons to one side, creating a negative side, leaving the other side positive. That difference in charge is a voltage. And we say it's an induced voltage because we've induced it by moving it with some velocity through a magnetic field. Alright, so let's go through one more example just to get the direction down. So if we move this conductor up, again, imagine a positive charge in the middle. What way is that positive charge going to be pushed? Thumb goes up, fingers, straight fingers go into the page, palm is pointing left. So the positive charges are going to go to the left, negative charges to the right. So the polarity of the voltage is positive on the left, negative on the right. And what would happen if this was then connected to a wire? Well, this is like a battery, right? It's got a voltage across it, and so current would flow through the circuit. You know, if you had a resistor here or a light, it would turn on. As you move this thing, the system, through the magnetic field, for example, let me just take those ones and put them down here. So we've moved it up a bit. This is where it gets interesting. Oh, let's just get rid of that. Bear with. So looking at the top box again, that conductor, which side will be positive? It's still moving up. The field is into the page, so it's still going to be positive on the left, negative on the right. But this bottom section is actually just a wire. So it's a conductor as well, like this whole thing. So it will induce a voltage, positive on the left, negative on the right. Notice how they are positive on the same side, negative on the same side. So no current will be able to flow, right? They'll effectively cancel each other out. And so since the whole closed loop is moving through the field, no current will flow. Alright, that's enough from me. Here's your homework. This is, what past exam question is it? I didn't write it down. It is a past exam question. I think 2016 or 2018, one of those. Middle track, magnetic field, connected to a power supply. So what happens when current goes through? Think right-hand slap rule. What's the force on the rod? Calculate the size of force. We remove the battery and we put wire outside the magnetic field. Why is a voltage induced? Right, explaining the idea behind the charges. And then calculate the size and direction of induced current. So if there's an induced voltage and the circuit is complete, is current going to flow? Right? Do you need a resistance? What's going on here? Here are some hints in case you get stuck. And here are the answers in 3, 2, 1. There you go. Alright, that was the final part of this small video series. Hope you got something out of it, and I'll see you around. Or probably not. See ya.